Oh, welcome back. It's Mr. Bennett here. Just sort of going through the next part of the operation. So what I've done in the notes, I've provided you a second example where you're using just numbers. So if we just scroll through that, again, you can see the key thing is you can see where I'm actually doing the row operation change. I'm actually got the term there, and then I show the working out over here. Alright, so going through there and solving that, so you can have a look at that in your own time. The notes will be on the website. So here is a typical question that you might get from an exam. Right, so sometimes you'll get to do your operation where you haven't been given the equation, you have to come up with the equation. Alright, so this one here is telling you a quadratic equation had 3 points, but we couldn't remember what the quadratic equation was. Alright, so what you can do is you can find the equation by substituting those points into the equation up here, the general term for a quadratic. Alright, so we want to know what our A, B and C values are. So putting it in there, the Y value would be -3, the X value would be 1, so that would make that A, B and C. Alright, when X is equal to 3, that will becomes 3 squared is 9, 3 times B is 3B, and that would be equal to -5 and so on. Alright, so the trick here though is to write this as an augmented matrix. So obviously that's going to be 1, 1, 1, -3, 9, 3, 1, -5, and then it'll be 4, -2, 1, -15. And as I showed you before, you would need to use your RRF, so I suggest that you try that on your calculator, make sure you get the right answer, and that would be telling me that obviously if I solve that, A is equal to -1, B is equal to 3, C is equal to -5, and so therefore my general equation for my quadratic would be -x squared plus 3x take 5. Alright, so very typical equation. We'll do some later in some more videos where you see some classic examples. Second little trick that you might see, if you get decimals like this, you're quite clear you can see they're all decimals. What you could do for this whole matrix is to times it by 10. Okay, so you're then working with whole numbers. So you can times any row by any value as long as you times the whole row by it. It might be that you only have row B, which is decimals, and so therefore you could times that whole row by 10. Or you could, in this case, times every row by 10. It just makes it a lot easier when you're doing your row operations to start dealing with whole numbers. Alright, so a little trick there for you. Now, this is the one I want to show you today. This is 9D question number 2 on page 375. So here is our augmented matrix already done for that. So I'm assuming you can do that skill. The tricky bit about this question here is we do have a value of K down the bottom here. This K value means that we can't use our RRF. Okay, we've got to do the row operation. So again, we just go through the process. We want to get obviously our triangle here of zeros. We want to get our triangle of zeros. That's what we're aiming for. Turn those things into zeros. Alright, so the first thing here, obviously with row 2, because it's 2 there, you go something like row 2, take 2 row 1. If you can see the setting out there, obviously doing that, you're going to get that answer there. So that answer there gets put back into the row at that point there where you're doing that row operation. For the last one, because it's 1 and 1, row 3 is going to be row 3 take row 1. So then that's going to be 1, 7, -1k take 1, 2, 1, 3. So when you do that operation, you get 7 take 2 is 5, -1 take 1 is -2, and then that will be k take 3. Alternatively, you could have had it the other way around where you had 3 take k. It doesn't matter as long as you're consistent with it. Alright, coming down to this next bit, obviously I want to get that next 0 here. Alright, that's what I'm aiming for. So in this case here, what I'm looking at is a term. So obviously because these two terms over here are in fact -5 and 5, to get a 0 there, all I have to do is add the two matrices together. Alright, so not matrices, add the two rows together. Must be early in the morning for me to say that. So obviously what we're doing here is we've got that. So when you add those two rows together, you got -5 and 5. You got 2 and -2, both going to give you 0, and then you got 5. You got k take 3 take 5. It's going to be k take 8. So this is my new row here. Now this is actually quite interesting in terms of how we solve that. The first thing you would have to say is 0, 0, 0 equal to negative k equal to 8. So generally what we're looking at is 3 dimensions, and we could be looking at trying to see whether these meet in a point or in a line. These planes meet in a point or a line, or these planes are parallel. Right. So the first thing is, does k take 8 equal 0 make sense? Well, if k is equal to 8, then we have an infinite number of solutions. In other words, that whole row would go out. Okay, so 0 equal to 0, that makes sense. So therefore, what it means is we would have this scenario over here where we don't know what our z is, so we'll have to let z be something and solve for that, and that would give us an infinite number of solutions. Now, if k is not equal to 8, then we have this idea, okay, where we have 0 equal to some number, which is inconsistent, and then we say that that basically has no solution. Right? That would be the case when, if we were looking at planes, okay, we would be looking at 3 parallel planes. Or if we're looking at lines, we're looking at 3 lines that don't meet. Now, this is what we call parametric form. Now, I'll just go through the process of this. The first thing that we need to do over here is we need to say let z equal t. Okay, so we don't know, we've got 3 unknowns, and we've only got 2 equations. Generally, you need 3 equations with 3 unknowns. Alright, so that's why we have to do this. So then what we do is we substitute that z value for t into this equation here for the y bit. So now we have 5 minus 5y plus 2z, 2t equals negative 5. So you bring that across and solve that. And a little bit of algebra, so you can follow the algebra that we've got here. Okay, you could come up with this equation here. Okay, so 1 plus 2/5 t is what we've got there. And then what we need to do is substitute our z and our y value into the original equation in row number 1, and we solve for that. Okay, so that's what our substitution there into the equation. Right, that's our z value. Okay, we're going to solve for that and bring that across over here. And what we can say, that doesn't look very nice, but what we have is we have an infinite number of solutions over here, and we could probably tidy that up a little bit, but I won't worry about doing it now. Generally, you'd want to present that as like this one here, where you've got a term over another term, or a term, so you'd probably make that 15 on 5. And so 15 on 5 take 10 would be equal to 5 plus 9t on 5. That would be a better way of doing it. What it really means is if t can be any value, so if t was 1, what would be the answer? Okay, if t was 2, then what would be the answer? So in this particular case, if we were looking at that, we'll go to the pen, we could say if t was equal to 1, then remember this term over here works out to be 15, that works out to be 5 plus 9t on 5. So that would be equal to 5 plus 9 is 14 on 5. This one here would be 5 plus 2 is 7 on 5. And then that would be 1. Okay, now we can make t equal to 2. And do the same sort of thing. We can make t equal to -7. We can make t equal to 1,000. T equal to 0. T could be equal to 0 in this case. Alright, so t could be any value, so that's why we have an infinite number of solutions. Now, if you refer to the yellow sheet I'll give you, that would be representation of the 3 planes meeting in a line. Got an infinite number of solutions for those 3 planes meeting in a line. Alright, so have a go at some of these questions from that chapter. Again, obviously, if you have an unknown in there, you must make sure that you use row operations. You don't have a choice. And we're equating things for, what makes sense. All right. So obviously, things like we have no solution. Obviously, when you have an inconsistent equation, we have infinite number solutions if we have our parametric form, like we've got here. And you can also have a unique solution as well, depending on how that works out as well. Alright, so good luck with those, and catch up with me if you need some help.